Hello, everyone. This is Edward Doolittle here with another Stat 100 lecture. We are winding up the course. This is Chapter 11, Analysis of Variance, that we're doing, and it is the last chapter of the textbook that we're covering. Fortunately, it's fairly short. We are only going to do a few sections from Chapter 11, and we're going to skip some of the details. So I think we'll be able to get through it in a pretty short time. I'm going to give my first lecture here on 11.1 and 11.2, and then we will go into the details, all the numerical examples in 11.3. So 11.1 and 0.2 are conceptual in nature, and then the actual practical calculation aspect we will look at in 11.3. This is not in the next quiz, so quiz 5, I should mention, is only on chapters 9 and chapter 10 of the textbook. So when you're preparing for the quiz number 5, you only need to study those two. Chapter 11 will appear on the final exam, though I can guarantee that. All right, so what are we talking about? Analysis of variance. Well, analysis of variance is sort of akin to when we did the comparison of two population means in mainly in chapter 9. Also, we did it differently in chapter 8, but in chapter 9 we did hypothesis testing around the difference between two population means. And what we were trying to figure out in chapter 9 is, are these two populations different? So we had the alternative hypothesis is that they are different, and the null hypothesis in chapter 9 was that they are not different. So that's the idea of ANOVA, only ANOVA, what we're doing is comparing 3 or more populations. And we're trying to see if there's a difference in the population means for three or more different populations. We will be using similar techniques, but they are a little bit more elaborate. The formulas are much more complicated, but we won't necessarily get into all the details about the formulas. I will explain that all in section 11.3. For now, let's just talk about some more general aspects of this. What we're doing usually here is an experiment. And experiments come in really two types. There's observation and there's experimentation. And these just talk about the ways in which we obtain our populations. So observation is where we simply categorize our experimental units into different categories. So we could be looking at men versus women, for example, or people from different nations, and so on. Experimentation is where we actually apply a treatment to different individuals. And this is very often used in medicine. So, for example, we're looking for a new vaccine or a new drug. What we will do is divide our group into several subgroups and apply a different treatment to each subgroup. So some might get the vaccine, some might get a different vaccine, some might get a placebo, and there could be easily 3 or more different subpopulations in this kind of an experiment. All right, so that's the kind of the general landscape, what it looks like. Now we're going to get into some details, some terminology about how these populations are designed and set up. Sorry, I just got to pull up my textbook here, make sure I'm giving you all the necessary terms. All right, so there are some terms in the textbook. You can certainly look at them there, but I want to go over them now in the lecture. There's a factor, a level, excuse me, a level, a treatment, and a response. This might be most easily communicated using an example. You can certainly look at the definitions in the textbook. But example 11.2 is kind of interesting. So we have an experiment where we have men and women, 20 men, 20 women. And then we also have, and that is observation. I mean, we are not giving people a treatment to turn them into men or women. So that is something that we merely observe. So that is back to this guy here, observation. On the other hand, we can give them a light meal or a heavy meal before we give them some kind of a test, say. And this is an experiment here. This is experimentation. We are supplying these treatments. And so what we will do is divide our men into two categories. Some will get the light meal, some will get the heavy meal. And we do the same thing with the women. Say there's 10 get the light meal and 10 get the heavy meal in each. So that's what this does, is it divides us into four different subcategories. So there's the men who received a light meal, men who received a heavy meal, women who received a light meal, and women who received a heavy meal. And so this categorization takes place along lines of factors. So in this experiment, there are two factors. There's gender, and there's the meal. And that's just to give you an idea what factors are. Other examples, factors might be a pesticide treatment that's given to plants. In that case, it's an experimentation. We are selecting plants at random and applying a chosen pesticide to some of them and a second pesticide to others. Or we may, again, look at factors that are observational. So we may divide people into categories according to their height, their weight, that sort of thing. And typically there are, well, I shouldn't say that. Let's just say, let's talk about level now. Here there are two levels. There's the male level and the female level. And it doesn't necessarily have to be, one is higher than the other, one is more intense than the other. It's just different. So each factor, in this case, has two levels. Here for the meal, there's two levels. There's light and there's heavy. And we could have added a third level if we had a bigger experiment. We had no meal, and that would be a third level. No meal. So if we had a third level, there would be now 6 categories: 1, 2, 3, 4, 5, 6 in our chart. Now, each of these regions is what we call a treatment. So here the treatment is women who had light meals. And here, the treatment here is men who had heavy meals. And so each of these spaces in my grids corresponds to a treatment. So here's the men with no meal, men with a light meal, men with a heavy meal, women with no meal, women with a light meal, women with a heavy meal. All right, so the number of different axes here is the number of factors. Each axis corresponds to a factor. There's the gender axis this way, and the meal axis is this way. How far you are along the axis is the intensity of or the level of the treatment. So here we go from no meal, light meal to heavy meal. We're increasing intensity of the meal treatment here, and here we have two different intensities of the gender treatment. So there are two directions that corresponds to two factors. We have in each direction you have several levels according to how far you move. Here are two levels. Here there's three different levels, and then a kind of a location, a choice of level for each factor gives us a specific treatment. And so there are multiple subjects, experimental units in each of these treatments. And that's what we're interested in this ANOVA is whether there's a difference in final outcome according to this, according to which treatment our experimental units received. Finally, one last definition. Response is what we're measuring, so we may give them, say, a test of some kind, a reaction test or something like that, and that is the response that we are testing in this investigation. And so what we want to be able to conclude from this is, say, that men who had a heavy meal have a different response from others in such a test. All right, so that's a general picture. Now we're not going to cover all of these kinds of possibilities in this course. We're just really going to give a gentle introduction to this concept of ANOVA. So one thing that we are not going to do is we're not going to look at more than one factor. We're only going to look at one factor. And so this is sometimes called one-way, a one-way classification. And so that is essentially 11.3 in the textbook. That's all we're doing. So multiple factors, I just talked about multiple factors to introduce the concept of a factor. So it's helpful, I think, to have two different factors so that you can see what a factor is in this example. But we are not going to do the mathematics and the statistics of two or more factors. It's much more complicated. We're just going to start with one factor. And typically there will be at least 3 intensity levels. Because if there were just 2 intensity levels, we could use the analysis of Chapter 9 instead of ANOVA. So we are going to look at examples in which there are at least 3. And there could, in principle, be 4, 5, 6, any number of intensity levels, but probably the problems that we will spend most time on will just have 3 intensity levels. That's enough to introduce the new ideas of ANOVA without going overboard with calculations. All right. So what are we trying to accomplish here? We are investigating. We're performing a hypothesis test on a situation like this. So there's a factor of some kind, and there's multiple intensity levels. And so these give us populations with population means. So we measure the response, well, not measure, but there is a response for this population. There's a response for this population. There is a response, an average response for this population. So we're looking for the average responses in each population, where the populations have received these different levels of this factor. And so an example that we're going to be using is lunch or breakfast. Let's just say breakfast to follow what the textbook says. Breakfast. Okay. So breakfast, you could have no breakfast, you could have light breakfast, you could have a heavy breakfast. And those are the three levels. And then we measure, say, students who've had each of these types of breakfasts. They form a population, and we're going to measure the mean response in some kind of test in that population. So that's going to give us our three different population means. And we are now going to do hypothesis testing around this. So our alternative hypothesis is easier to write in words than it is in symbols. We're going to say that at least one of the population differ from the others. And the null hypothesis is easy to express in symbols. It's that they are all the same. All right, this is what ANOVA does for us. It tests these two hypotheses. It tests the alternative hypothesis versus this null hypothesis. So all that ANOVA does is to tell us whether there is a population that differs from the others. That is all. It doesn't tell us which population. It doesn't tell us more or less. It only tells us whether one differs from the others. And then you may be interested in which population differs. Does this drug actually have a positive effect for our patients? Well, you have to do that after you do the ANOVA. So you first do the ANOVA to see if there's any difference. If the ANOVA says that there is a difference, then you use a different test to try to find out the nature of that difference. That's something called a post hoc analysis, and we are not going to be doing that. There's a little section in the textbook about it, but I think we'll have to skip that. Anyway, once you know that there's a difference, then you can try other techniques to find out what is the nature of that difference. Is one better than the others? Are all three really different, or are two the same and one different from the others? Those are kinds of questions you can ask post hoc. Post hoc means after this. In Latin, it just means after we do this ANOVA test. Then we can do the rest of it. If the ANOVA test tells us or if we're accepting the null hypothesis, then there's no difference, then we won't benefit from doing a post hoc analysis. We'll just have to skip that. All right, so that's how ANOVA works. That's the big picture. It's just a hypothesis test comparing two very simple hypotheses, and it gives a simple answer. And when you draw your conclusion from ANOVA, you have to say one of two things. You say either that there is one population that differs from the others, or no, all populations are the same. Okay, how does ANOVA do this? Well, here is kind of a picture of two populations, and Here we can eyeball them up. We don't need any fancy statistical tests, although it would be better if we did use our statistics. But I mean, even anybody can look at this and say, well, the mean for this population looks like it's different from the mean for this population. So this is a sample, of course. So I'm using my sample to kind of stand for the population. But if the sample's large enough, maybe 3 isn't big enough, but anyway, if a sample is large enough, I can detect the difference between these two populations. It seems pretty clear in this case. But what might happen, what interesting phenomenon can happen, is that here's one population and here's another population, and they overlap. They're kind of interwoven. Now you may say, well, I still can see the difference between these two populations, but it really is harder to see, and it's harder to be convincing about yes, I've established that there really is a difference when they're overlapping like that. So that's what ANOVA is going to try to do. It's going to try to detect this kind of a situation where even if the populations are interwoven, we can still find enough of a separation between the two to convince ourselves that or convince ourselves and our readers and our bosses and so on that there is a difference between these populations. And of course this is complicated by there may be multiple, not just two, but there may be multiple different populations, so 3 or more. Okay, so how are we going to do this? Well, we are going to do a very careful analysis of the variances. So the variances, the population variances for population 1, population 2, and population 3. We are going to take the variation that we see in the total variance that we see, and kind of split it up or apportion it among the 3 populations. And we're going to also try to attribute some of it to error and some of it to the treatments. So that's what we're going to do. We're going to look at all the total sum of squares of variation in our samples, actually, not in the population, but in the samples. And we're going to try to attribute it to, divide it, split it into between treatments and error. So error is just random variation noise that appears in any experiment. And treatments will be the variation that's due to any actual difference in the treatments. All right, so this is not entirely clear. It will become clear once we start talking about formulas and so on. But that's just to give you a general flavor of how it goes. Finally, we have to, as always, look at the assumptions we're making, because you don't want to be applying a statistical test where it's not valid. Then if you do that, you can't trust your conclusions. So we make certain assumptions in ANOVA, and some of them are actually kind of strong. So similar to the t-test, or small sample, we're going to assume that the populations are normally distributed. Sometimes we can get away with weakening that as long as they're roughly mound-shaped. And another thing that will help us is that the samples are roughly the same size. So if we don't have this second condition, then the test becomes very sensitive to violations of the first condition. What we want are samples that are roughly the same size, so that even if there is a small departure from normality in the population, it's not going to affect us so much. Finally, there is a rather strong assumption here, and that's that the variances are common, are the same. Population to the next. So the variances are the same for all of our populations. And that is a fairly strong assumption, but it does hold true in enough cases that this can be a useful statistical technique. And there's also, a general issue about how do we make a random sample. If we are just observing, then it's easy to make a random sample. If we are designing an experiment, it becomes a little more tricky. But we have to give some thought, and we're not going to go into great detail about this, but how do we apportion different treatments? So in the case of lunch, we kind of have to randomly put our experimental subjects into different categories. And here you're getting no lunch and you're getting a light lunch. And it can't be based on something that could introduce bias. So it can't be based on, say, the order in which the students entered the classroom. That might be biased somehow. There has to be some kind of randomization. The same thing if we're doing tests of, say, pesticides on different plants. It probably isn't wise to just give the first 5 plants one pesticide and the next 5 plants another one and the next 5 plants another one, because there could be kind of a bias introduced by the way that we are, the way that the plants are arranged already means that there's some kind of there may be some kind of difference between these two. Some might just be getting more light than others because they're arranged in a certain order. So we want to take away that potential source of bias by randomly assigning plants to the different treatment groups and so mixing them up. And there's certainly a lot of work been done on statistics of how we mix things up. Again, we're not going to go into details. We're going to assume that our experiment has been properly designed when we analyze the data. So we're just going to look at the data analysis part of this. All right, so that is an overview, a bird's eye view of ANOVA. We will get into all the nitty-gritty details in 11.3. There's lots of formulas, but I'm going to try to boil it down to its bare essentials so that we can finish this thing off once and for all. All right, so thank you for listening. I will be back in a little while with 11.3.